We, all right, let me, a couple things, just a reminder. Where am I? Here we go. Let's look at the calendar from Canvas. Okay, today's the 24th. Obviously, no class on Thursday. We have Thanksgiving. Next week, the plan is today we'll finish up chapter 14, and then next week finish chapter 15. The first, that would be the last chapter for the semester. It's a very short, probably take us half the class time period. So that leaves, whatever time you guys want, what's left next week to do study or questions. Also, the third, we have study dates. So you have a lot of study days to help you out here as far as if you got questions. Now, the fall in December, don't forget that activities coming up. You got homework coming up. On the 8th, you have exam number 5, which is homework 13 through 15. Okay, and so I spread out the homeworks here pretty far to help you out. Let's see, that means on the 8th, again, basically would be a study day because we'll be done with the chapters the previous Tuesday. And so we have part of next Tuesday, the following Thursday, the following Tuesday and Thursday, time for you to help you review. I will see what I have with respect to any type of review things I can go over, but there is on the site, on the course site, a practice test for the final. I suggest you download it, take a look at it. Be very exam questions be very similar. In fact, all the final exams questions be very similar to what we've done already with respect to exams 1 through 5. So you'll have plenty of time to ask questions and get help from me if you need it. Okay, if things are going fine, don't forget to keep up with the homework and so forth, activities. If things are going fine, that's great. Just continue doing what you're doing. There is an extra credit, tentatively it's been said to be due on the 18th. I may have to shift that because we're having to get the grades in a little bit earlier than normal. But it is a extra credit. It's assigned to the final exam section. So whatever points you gain, which I believe will be 15 points, go into the extra credit section, into the final exam section. And so there's one way to pick up some points. If you don't do too well in the final, the extra credit will help you out there. But that's a file, digital file, if you will download it, take a look at it. There's a link in there that sends you to the simulation software that deals with density. And basically you are taking blocks with different material, you are weighing them, or they're in constant weight, and then you're calculating the volume, or they are in constant volume. With that information, you calculate the density. Basically, you grab a block and immerse it into a container that has liquid to determine its volume. Just remember to immerse that cube completely into the liquid. There are some things that float that would not give you the exact volume of that cube. Also, when you're asked to calculate the volume, remember you are looking at the difference of the volume in that container. These cubes are small. Your cubes will not displace over 100 milliliters of volume. Probably somewhere from maybe 10 to 30 milliliters of volume for these cubes. And so just remember, you are subtracting the container of liquid has an initial volume. You immerse the cube into the container. You have a final volume. That difference is the actual volume of the cube, the actual volume that cube displaced. Okay. So keep that in mind. Completely immerse the cubes and make sure you actually use the volume of the cube. All right. So that's enough for the extra credit, extra credit assignment there if you want to do it. Any questions? No?
I think I'm good. Thank you.
Okay. All right. That's good then. Well, I wrote on my notes that we ended up with we stopped at not chapter, page. We are in chapter 14. We stopped on page 14, where this whole chapter deals with intramolecular forces. These intramolecular forces are very important with respect to how chemicals react, how they behave out in whatever function they're doing, as far as its properties are concerned, why certain things have a boiling point at a certain temperature, why certain things flow at a certain rate, things of that nature. And they're all related to the intramolecular forces, not to be confused with the intra. There's inter, did I say that wrong? Inter, those are forces, I-N-T-E-R. Those are forces that occur between molecules, and these are molecules with each other. Those are those forces, as compared to intra, I-N-T-R-A, forces, which actually deal with the bonds of the particular compound. And so we had two types of bonds. We had covalent bonds and ionic bonds. Okay, ionic bonds are a combination of a metal and a non-metal. They have a full-fledged negative and a full-fledged positive charge. They come together much like two magnets, okay, electrostatic attraction. There's no sharing of electrons. And we use the term bonds, but in this true sense of the word, it's not really a true bond, okay? And hence the term ionic bond. It's really an attraction, but nevertheless, that's what we call it, ionic bond, metal, non-metal. Covalent bonds consist of two nonmetals. The difference here between ionic and covalent bonds, to refresh your memory, is that there is a sharing of electrons between two different elements. Now, we have two types of covalent bonds. We have polar and nonpolar. The nonpolar bonds are basically two atoms that are the same, and therefore have an equal amount of electronegativity. Therefore, there is no pole there. There's no positive or negative. It's nonpolar. Okay? Now, when one of the atoms is different, and there's, again, a covalent bond, when you've got two different atoms, we have a polar bond. And these polar bonds, with the exception of carbon-hydrogen, though they're different, they are nonpolar bonds. But other than that, those carbon-hydrogen, you create a polar bond. Now, in which direction the polarity goes to depends on the electronegativity of the atom. And the one with the most electronegativity just tells you that that's the direction that the electrons are being pulled. So those electrons that normally in nonpolar bonds are being shared equally, in polar bonds, that sharing is not equal. One element is pulling the electrons further onto itself more so than the other, okay? Now, refresh your memory on those bonds, because once we know about the type of bonds we have, we can then determine whether the whole molecule is polar or nonpolar. With respect to nonpolar bonds, regardless of how many or what you have, if all the bonds are nonpolar, then we have a nonpolar molecule, okay? Now, with respect to polar bonds, 9 times out of 10, when you have polar bonds, you end up with a polar molecule, unless the polar bonds, the polarity of the polar bonds cancel each other out. Carbon dioxide is a good example, classic example. We have two polar bonds, two carbon-oxygen bonds. They happen to go in the direction opposite of each other. Therefore, they cancel out. and therefore, with the polar bonds canceling out, you have a non-polar molecule. Okay. When you're in tetrahedral position, you have 4 polar bonds. That position, the configuration, those 4 polar bonds that are the same cancel each other out. Therefore, you have a nonpolar species. Okay. So whenever you have polar bonds that do not cancel each other out, then you have a polar molecule. Why is that important? Because that's going to allow us to define and to assign the type of force that molecules have. We have 4 forces to work with. The first one is called London forces, London dispersion forces. Only non-polar molecules, when it comes to forces, that's the only force they have. They have nothing to do with dipolar, okay? So non-polar molecules all have London forces. Now, dipole. Well, in order to have dipole, you must have a polar molecule. So therefore, you have polar bonds that do not cancel out. Okay? Now, when you have a hydrogen bonded to either a nitrogen, an oxygen, or a fluoride, yes, they do have dipole bonds. But this is a very unique case only for those 3 atoms, nitrogen, oxygen, fluoride. When they're bonded to hydrogen, they have a very additional force that we are called hydrogen bridging force. Okay, so yes, there is a dipole between nitrogen and hydrogen. However, that interaction between those 3 elements and hydrogen result in an additional force called hydrogen bridging. Now, with respect to strength, London forces are the weakest, hydrogen bridging are the strongest, and dipole is in between the two. They're not as strong as a bond strength, but nevertheless, they have a hefty strength. Okay. Now, the other force, the last force, is called ion dipole. Ion tells you, hopefully, that you're dealing with an ionic compound, a metal-non-metal combination. And the dipole deals that you're dealing with a molecule. In this case, since you are dealing with an ion, then you're dealing with an aqueous solution, which would be water, which is a dipole, has a dipole in it. It actually has hydrogen bridging force in there, okay? And so normally, if you see an ion and you're dealing with water, then the only force involved there is an ion dipole force. Okay. So let's take a look at here. We got a table. We got the first column. We have 1, 2, 3, 4, 5 molecules. Okay. We're being asked to determine whether it's dipole, or excuse me, polar or nonpolar. And then once we determine that, that allows us to assign to it which IMF interaction it has. Okay, carbon dioxide, which this means that if you recall that, way back when we were doing Lewis dot structures, well, go refresh your memory on that, because in order to determine whether something's polar or nonpolar, you may need to require to draw a structure and using the shapes table, okay? Now, we did talk about carbon dioxide, and we did demonstrate why carbon dioxide is nonpolar, because the dipoles cancel out as far as the polar bond, okay? So therefore, carbon dioxide we define as a nonpolar molecule because the dipoles cancel each other out. Being nonpolar, the strongest intermolecular force that they work with are London forces, which is really of the 4 the weakest, okay? Now PF3, if we go and use the Lewis dot structure to determine the structure of this compound, we'll find it to be very much like ammonia, NH3, all right? And we'll also find it to have lone pair of electrons in the central atom, just like nitrogen, NH3. And if you recall way back when I said, anytime you end up with a lone pair of electrons on the central atom, automatically you got a dipole compound. You got a polar molecule. And you certainly have one here with difluoride, phosphorus difluoride. Very polar, okay? As far as IMF interaction, the only thing you can have is the dipole-dipole. You don't have any London bridging because there's no hydrogen involved here. Okay, HF, classic example of a dipole molecule, very polar. Okay, it's covalent, very polar. We have a polar species. Okay, now, so we figure out which IMF. Well, it can be ion dipole because there's no ion associated here, no ionic compound. It's not London forces because it is polar. Okay, now the only determination is it dipole-dipole, hydrogen bridging? Well, could be dipole-dipole, but it is hydrogen bonded to fluoride, NOF, not on file. Remember, nitrogen, oxygen, fluoride. Anytime you have hydrogen bonded to those three elements, you end up with hydrogen bridging force. Okay. Carbon hydrogen, you got tetrahedral species here. We got carbon hydrogen, which are nonpolar bonds. There's 4 of them. Very, very nonpolar species. It's a hydrocarbon. All hydrocarbons, nothing but carbon and hydrogen, are always nonpolar. Being nonpolar, the only force associated with that would be London forces. Finally, the last one, you got Ki, potassium iodide. You got AQ in parentheses, which tells you it's aqueous. It's ionic in polar water. That's all you can say about polarity. It's an ionic compound. And because you're dealing with ionic and polar water, the only thing you have with respect to IMF interaction is ion dipole. All right. Well, what they're saying here is they're talking about what's called Coulomb's law. And we're just going to very briefly touch on this. There's not a lot of information to really learn, but you're probably already familiar with this because I'm sure you've taken, let's say, magnets, and you've seen how you put 2 different magnets and you bring them close together, the positive and negative, boom, they attract very quickly the closer you get them together. And if you try, for example, let's say putting 2 south together or 2 negative or 2 north together, they will repel, correct? And if you bring them together, 2 souths or 2 norths, you can feel that force of repulsion, how they repel each other. And the closer you get them together, that stronger, that force becomes even stronger. Even the other way around, where you got 2 magnets, if you have them, this far away, you don't really feel that force of them attracting each other. But as you bring them together, you can actually start feeling that force of attraction. You got them real close together, boom, they hook up very quickly. All right, so that relationship is driven by what we call Coulomb's law. Now, I know there's a lot of information here, but the thing just for right now, just to set aside, the only factor we're really concerned about is F, meaning force, and R, which is the radius between 2 of these species. Q1 and Q2 just happens to be the charge of them. So I can have a positive and negative charge, okay? And Ke happens to be a constant. But what I can do is simply just combine the Ke, the Q1 and the Q2 and put them all together and hold that constant and just call that A, just for argument's sake. And so what this does is I can simplify this equation and say that the force between 2 charged species is simply A, which is the combination of all those constants Q and K, divided by the radius between them square. Okay? Now, all right. Now, if I hold the A constant, and let's just say for argument's sake, I call R equal 1, okay? Well, if R equals 1 unit, just say for argument's sake, R equals 1 unit, obviously F would be equal to A, right? Because the 1 squared, 1 times 1 is 1. So A divided by 1 is A. Okay. Now let's take, so the force is equal to A, whatever A is. All right. Now, if I take that same radius where it was 1 and I double it, now I got force A divided by, we doubled the force, so it's 2 to the second power, or 2 square. What is 2 square? 2 times 2 is 4. And so by increasing the radius by a factor of 2, guess what happens to the force? The force now has been reduced by 1/4 of A, right? 1/4 of A. So that whole force has been reduced by 1/4, just simply by doubling the distance that I have between the two charges, okay? The converse is true in that I can reverse it, and instead of doing, instead of doubling, I go reduce it by half, okay? And so reducing it by half, I go from 0.5. 0.5 square is 0.5 square. Oh, hold on 1 second. 0.5 is 1/2. So 1 divided by 0.25 is 4. And so if I reduce that force by half, so now I got 0.5 squared. Now I got A divided by 0.5 squared, which would be what, 0.25? Okay, 1 divided by 2.5. That means my force would be increased by a factor of 4 by reducing it by half from where I started at 1. And so yeah, my force, by increasing my distance by 2, my force is decreased by a factor of 1/4. And by decreasing radius by half, my force is increased by 4. And that's basically what this is trying to say, is that the attraction between two charges is proportional to the charge magnitude and inversely proportional to the distance square. Inversely proportional means, directly proportional means if one variable goes up, the other variable goes up proportionally. Inversely proportional means if one variable goes up, the other variable goes down, okay? And so in this case, inversely proportional, the charge, the attraction, is inversely proportional to the distance squared. Okay. All right. Oh, hold on. Let me clear this. And that's basically all we want to take away from Coulomb's law. Basically, the closer we get, the force gets stronger. Further away we get, the force gets weaker. Okay. All right. Let's take a look at this table here. And there's a series of questions, and then the answer should be, well, are we talking about the bond or are we talking about the IMF interaction? Okay. And so you got to read these questions carefully. Let's take the first one. What holds the atom together in one ammonia molecule? You think they're talking about the bond or IMF? What do you guys think?
The bond.
Exactly. The bond, because they're saying one ammonia. Okay, so we are talking about specifically ammonia, which NH3, which is a polar covalent bond. Okay, now here to ask you, the next one is, what is holding the sodium ions in water? Okay, sodium ions in water, we're talking about those 4 forces. We got ions, we got water, which have a dipole. Guess what? It is the ion dipole force. The ions from the salt, okay, and the dipole comes from the water. Third one says, what is holding 3 hydrochloric acid molecules together? Do you think it's the bond or IMF? The question here. IMF. Exactly, because they're talking about 3 molecules. All right, well, to answer that, then we got to answer the next question. Since we determined it's IMF, which IMF? It's not HCl is polar, right? Everybody agree on that? So it's not London forces. It is not ion dipole because there's no mention of ions here or water. So the only thing left is either hydrogen bridging or dipole-dipole.
Dipole.
Got it, dipole-dipole. Because if it was hydrogen, you might say, oh, hydrogen bridging. Well, remember, hydrogen bridging only applies for hydrogen, which we have here, that are bonded to nitrogen, oxygen, and fluoride. So that's correct. So sometimes you got to go through a systematic approach and eliminate the stuff that's out there so you can come to the answer. And that's okay. Go at it, systematic approach, eventually get to the point where you just look at it and you recognize it. But go through your steps here. What is holding the ions together in salt or sodium chloride? Okay. Are we talking bond or IMF? What do you guys think? What is holding the ions together in salt or sodium chloride?
A bond?
Exactly, okay? Because we're not talking about a solution because there's no mention of water. And so we're talking about together. So what kind of bond could we be talking?
An ionic bond.
Ionic bond, exactly. Can't be anything else, can't be covalent because sodium is definitely not a nonmetal. Okay, so we got ionic bonds. Here, next question is, what is holding 4 H2O molecules together? So now we are talking about IMF because we're talking about 4 water molecules together. What force are they dealing with? Okay, so we know water is very polar. Okay, also there's no ions here. The fact that it's polar means no London forces is not an option. No ions associated here, so we can take out the ion dipole. And so we got left dipole-dipole and hydrogen bridging, right? So which one would it be?
The hydrogen bond?
Hydrogen bond, bridging, yeah. Now, yes, they still use the term hydrogen bonding. You'll find some textbooks that use that. They're trying to go away from the term because it's not really a true bond as we think. So they're trying to use the word hydrogen bridging. So, but if you say hydrogen bonding, obviously that's acceptable because I'm more familiar with the term hydrogen bonding than bridging. So it takes a while to get that bridging in there. So yes, hydrogen bridging forces involved. What holds nitrogen molecules to each other? So we're talking about IMF, right? Okay. So what do you think is holding nitrogen gas molecules to each other?
The London?
Exactly.
Switch?
Yeah. How'd you come up with London though?
Because the the N2, which is the 2 nitrogens.
Uh-huh.
And my understanding is if they're equally shared, then they would become nonpolar.
Got it.
Okay.
Yeah, you sound unsure. Go for it. You got it. It's nonpolar and that's it. Okay.
All right. I get nervous. I'm sorry.
No, don't get nervous. It's nonpolar. You got it. Being nonpolar, the only force you got to deal with is London forces. Okay. All right. So second one here, almost second to the last. What is holding the oxygens together in an oxygen gas molecule? And so are we talking bond or IMF?
Bond.
Exactly, a bond. And what kind of bond are we talking about?
Covalent.
Covalent bond. Can we further characterize it?
Non-polar covalent.
Got it. Non-polar. okay? Because again, like nitrogen, we got two elements exactly the same, they're equal sharing, okay? Equal sharing. I already showed you the hydrogen bridging. So here we have, the last one is what is holding two ammonia molecules together. Again, we're looking at IMF interactions. Definitely not, we know that ammonia is very polar. That's the NH3 formula, very polar. So it's either going to be dipole-dipole or London bridges. Since it's nitrogen bonded to hydrogen, part of the three elements, so definitely hydrogen bridging forces. Okay. I do emphasize the fact that yes, those nitrogen, oxygens, and fluorides that have hydrogen, that yes, they do have dipole-dipole interactions. However, they have a special case, special extra bond, if you will, because of the interaction of nitrogen, oxygen, fluoride, and hydrogen. It's called hydrogen bridging. Okay. This flow chart a little bit crooked, but it should give you the gist of what we just did. One, with respect to IMF interactions, if it's we know it's going to be covalent. Okay, we're dealing mostly with covalent bonds. If it's nonpolar, no questions need to go any further. It's London forces, plain and simple. That's the only one. They're the weakest forces too. Now, if it's polar, obviously, if it's nonpolar, then it must be polar, right? It's only got two choices, polar, nonpolar. If it is polar, and we're not dealing with any ion with respect to, say, sodium and water, then we can eliminate the ion-dipole interaction, okay? If it's polar and it's not hydrogen bonded to either nitrogen, oxygen, or fluoride, we can eliminate the hydrogen bridging, and the only thing left is dipole-dipole, okay? Dipole-dipole. So there's a flow chart to help you out with respect to the IMF interaction. Now, why is this important to learn this? Because we now are going to take that, we started with building the molecules, figure out the polarity, whether a molecule is polar or nonpolar. Now from that, we talked about well, we did talk about the bonds, but we've been talking about the IMF interactions with respect to nonpolar versus polar molecules. And we're going to utilize this information to be able to compare and contrast these properties. Vapor pressure, okay? Vapor pressure, if you got a closed cap of, so let's say a soda pop, we all know they got pressure in that empty space. If we were to put a meter on that empty space, we can measure the pressure, okay? And so IMF has an effect on vapor pressure, whether it's high or low, okay? With respect to boiling point, that is the temperature in which a molecule or compound will go from the liquid to the gas phase at 1 atmosphere. Water, for example, boils at 100 degrees. Other things like ethanol may take, say, 78 degrees Celsius. All of that's related to the IMF interactions of these molecules that they have with each other. Surface tension. I'm sure you've seen this. Your car is dirty, like mine most of the time. You throw a little water on it, the water just spreads out, okay? Let's compare, you take the car, wash it up, you got a little wax job on it, you put water in it, it beads out. Well, that measure of beading, the flatness or beading up, is called surface tension. IMF has a factor on that, how we can compare and contrast the surface tension of two different molecules. And viscosity, basically a measure how thick a material is with respect to, say, flowing. We all know that honey, for example, flows at a slower rate than, say, water, okay? And we also know that that same honey, if we want it to flow faster, what do? We heat it up. And by heating it up, guess what we do? We break up those IMF interactions between the molecules that allow it to now flow a little bit faster, okay? So we're going to be able to compare and contrast. Now, we can't determine absolute values. We can't say, based on the structure, based on IMF, the boiling point is whatever value. We can't do that. What we can do is compare one molecule with the other. And even that comparison, we can only say, well, this molecule would have a higher boiling point than this molecule, or this molecule would have a higher surface tension than this molecule. Okay? That's what we'll be able to do with that information. So I did talk about the vapor pressure. Okay, and these are a closed container. If the molecules, if the liquid phase is holding on to their molecules tightly because of their IMF interactions, then guess what? The vapor pressure is going to be lower, right? If they're not holding on to them very tightly, vapor pressure goes up for a closed container. We also know too that if we take the cap off or take the lid off, all the liquid will evaporate. Okay, molecules in the liquid phase are moving; they're dynamic. You know, you think about it. I got a cup of water. I leave it on the kitchen table for a couple of days. What happens to it? Guess what? It evaporates. Well, wait a minute. How did it evaporate? Well, I didn't even heat it. We all know we put it on the stove and heat it up, it's going to evaporate, right? But how does it evaporate? By just sitting on the kitchen counter. Well, it does that because the molecules are moving, constantly moving in the liquid, even in the solid phase, but not as much. So in the liquid phase, so those molecules that are near the surface, and you have water molecules, let's say we're talking about water down here in the bottom of the surface, as it moving, it could hit another molecule near the surface and give it enough energy to kick it into the vapor phase. But this occurs constantly. Eventually, all that banging around causes all the gas molecule, all the water liquid to essentially evaporate without having to put any energy into the system. It's simply because these molecules are constantly moving, constantly moving. Okay, now, you know, we got vapor pressure because if you take that soda pop and what do? You keep it close and you shake it up. What happens? The gas pressure goes up, right? If you take that cap off, you get a big mess. Okay, because more gas molecules go into the gas phase, into that open area, and pressure goes up. You know, just like putting air in your tires. Where do you go? You go to Quick Trip, go to pump up your tires. What are you putting? You're putting more molecules of air into your tire. Guess what? Pressure goes up. Okay. All right. So if we have strong IMF interactions, IMF forces, our vapor pressure gets lower. Okay. Think about that. If our IMF interactions forces are strong, we hold on to the molecules, they hold on to each other very tightly, which means that less molecules are able to go into the gas phase. Okay, so this diagram kind of depicts that. We can see that A has a weaker IMF, okay, because there are more gas molecules in the gas phase. There's more spheres in the air, okay, compared to B, where there's less material in the air in the gas phase. So this suggests that A has a weaker IMF interaction forces, and B has a stronger IMF forces. Okay, which tells us that A would have a higher vapor pressure because there's more gas molecules in the gas phase compared to B. Okay, all right. Boiling point. Okay. Strong IMF, higher. If we have a higher boiling point, means that we're gonna have strong IMF. Okay. Again, same reasoning why vapor pressure. If the molecules are held onto each other tightly, it's going to take a lot of energy to drive them into the liquid phase, into the gas phase. So water boils at 100 degrees. That's pretty high. 100 degrees Celsius, that's a lot of energy to get that water to boil, 1 atmosphere, compared to acetone. Acetone, as you know, or fingernail polish remover, you open that cap and you can smell it. Very volatile. Those IMF interactions are very weak, and therefore the molecules very readily go into the gas phase, the liquid molecules. Surface tension, similar scenario. Okay. If we have strong IMF interactions, then our surface tension will be higher, much higher, compared to a molecule that has a lower IMF interactions. We will have something like A. Those water molecules will hold on to each other much greater than the ones in B. So the ones in B basically kind of flatten out compared to A, which beat up more. Okay. So we can predict, again, surface tension, relative surface tension. Viscosity, that is the ability to flow. Okay, so we know that oil flows slowly because of its high viscosity compared to, let's say in this example here, vodka or water has a low viscosity. It happens to flow rapidly. So having strong IMF interactions would result in having higher viscosity. Again, because the molecules are holding on to each other at a greater force. Okay. All right, let's compare two molecules. And this is where we talk about we can only do a comparison. We're going to compare ammonia with fluorine. Okay. And this is where we need to start. You know, we started way back when where we took the names of compounds to create formulas. So we got to write the formula and determine from the structure that we come up with whether something is polar. We talked at length about ammonia. We know that it's a polar species. Here's the formula, NH3. It's got a lone pair in the nitrogen. And we see fluorine diatomic. Okay, that tells us something now, right? Plus, we got nitrogen and hydrogen. So that means that the forces for ammonia are hydrogen bridging. And for fluorine, since it's diatomic, very nonpolar, okay, London forces. So the London forces are the weakest, hydrogen bridging are the strongest, and dipole-dipole somewhere in the middle. So already we can do some predictions of properties just by knowing the force of the force that each molecule has in its depending on the structure. Question number one: who has a stronger IMF? Well, we just discussed that. Ammonia does. Why? Because it has hydrogen bridging, which are the stronger forces of the three. Okay. Which has the lower boiling point. So you got to think about this. I got to compare ammonia and fluorine. I'm looking for the lower boiling point. So that would mean the one with the stronger or weaker IMF. Which one do you think I'm looking for? Who do you think is going to have the lower boiling point?
I would probably say ammonia.
Ammonia has the lower boiling point?
I mean, that's just a guess. I don't know.
Well, don't guess. Don't guess. Think about it. Who's got stronger force?
Fluorine.
Ammonia. What's that?
Fluorine has the strongest force?
Yes. Okay. That means that those molecules are holding on to each other much greater than the molecules are with the fluorine.
Mm-hmm.
Okay. Which means the one with the lower boiling point would have to be the one with the weakest force, which would be fluorine. Okay. Remember, the strength is the London forces is the weakest, hydrogen bridging is the strongest, and dipole-dipole is in between the two. Okay. And for something to have a low boiling point, that's the temperature that they go from a liquid to a gas. To have it low, they're going to have when I'm comparing two molecules, they're the ones that have the weakest force. In this case, the London force is the weakest. Therefore, fluorine will have the lower boiling point. Okay. We already established which one is polar, and that's ammonia. Okay. Now, think this one through. Which has the higher vapor pressure? Okay. Now that means the vapor pressure is that point where you have, let's assume we got liquids of both of them are in liquid phase and it's in a closed container. And so I'm going to have more material in the gas phase in the closed container. So its vapor pressure will be higher. Again, in order to have more material in the gas phase, you got to have weaker forces. So which one is weaker here, London or hydrogen bridging?
London.
London is the weaker force, which means there are more molecules in the air, just like that. Okay. Notice that in A, there are more molecules in the gas phase. So it has the weaker IMF, which means it has a higher vapor pressure. There's more molecules in there compared to B. Okay. Let's go back.
In order to answer these questions, I have to figure out their bonds or their forces first, and then
Yes.
from there I can, okay.
Right. Once you figure, well, first you got to figure out from Lewis dot structures or from memory of what they are structurally, whether they're polar or nonpolar. So it's diatomic, you know, the diatomics are going to be London forces automatically. The NH3 you may not remember, so what I got to do is go to Lewis dot, draw the Lewis dot structure for NH3. And I end up with a lone pair of nitrogen, which tells me I got a polar molecule. The fact that I got a lone pair in there. In fact, I said anybody in group 5, nitrogen, phosphorus, you're in group 5. When you write molecules for them, they're the central atom. They're always going to be lone pair. Group 6, always going to have 2 lone pair on the atom, on the central atom. Okay, which has a higher vapor pressure? Again, fluorine, because it has the weaker force. Okay, and then which is the least viscous? Let's assume they're both liquids, and it's possible for them to be liquids under certain conditions. Which one will be least viscous? Which will flow more readily? Ammonia or nitrogen? What was that? Yeah. Uh-oh. Somebody's upset. Fluorine is the least viscous, okay? Because it has the least force. If it was the most viscous, then the one with the stronger force, just like honey and water. Of the two, honey is more viscous, which implies that whatever forces IMF interactions occur for honey, they are stronger than they are for water. Otherwise, they would flow just as much as if they were forces were the same, they would flow just as well, just the same, liquid or honey. Okay. And the more surface tension, the ammonia. Again, the same thing. Surface tension, think of beading. So if something beads up, that means the molecules are being held on closer together than something that doesn't bead very well. And you put it on the surface, it spreads out. Okay, so ammonia has a stronger IMF. So it would bead more than chlorine. Okay, because it has hence has the higher surface tension. Okay, so thing to remember, this will help you out. Now here we're talking about if IMF increases, our viscosity increases. Think about that for a second. As we increase the IMF, the strength of the IMF, our viscosity increases because the molecules are being held onto each other much tighter than those that have the weaker IMF. Okay? Same is true for the boiling point. The fact that the molecules are being held down closer and tighter with each other with those forces as the IMF increases, our boiling point increases. So does our surface tension. Okay? The only thing that does not increase is the vapor pressure, but because of the same reasoning. Because if the IMF increases, then we're going to keep the molecules tighter in the liquid phase, and less of them are going to be going into the gas phase. It's like that diagram of A and B, where there's more molecules for A than there are for B. Okay? And B has the less molecules in the gas phase. Now, all right, any questions about this scenario? Now, notice it said as IMF increases, but the wording could have been if IMF decreases, then all the answers would be the opposite, right? Okay, so read the questions carefully. All right, let's talk briefly about water. Water is very unique. It is, we went through this as far as the Lewis dot structure. It has a bend geometry. Its bond angle is much, much less than 109.5. It has two bonded pair and two lone pair. Water is extremely, extremely polar. It literally dissolves almost any ionic compound. Now, there are degrees of solubility. Remember from the solubility rule, some of them are insoluble, but even those classified as insoluble still had some material in solution. There were the weak electrolytes, okay? So water is very, very soluble. It will dissolve literally everything. Some very quickly, other things take more time. Now, water has very strong hydrogen bridging force between the molecules, very strong. So it's very polar, extremely high IMF interaction, has a low vapor pressure because of the high IMF. Its boiling point is 100 degrees Celsius, and its freezing point or melting point is at 0 degrees Celsius. Has extremely high surface tension. And the other thing that's unique is that when water freezes, it literally expands. And when it expands, the density, which is the ratio of mass over volume, for a given unit amount of water, when you freeze it, that same unit of water expands. So its denominator, its volume gets bigger, so we end up with a density much less than water, much less than 1, which means that ice will float, okay, simply because it expanded and changing that ratio. So it's very unique. When it does freeze, it does form this crystalline structure, which is interesting about nature, is that it tends to prefer that 6-membered ring, the hexagonal shape. And something unique that I don't quite follow, I've tried to figure for years, is why snowflakes are all different. Okay, there's a picture there. So it was studied for many years, and one couldn't, still haven't figured out why. I'm sure there's an answer out there. Okay, let's take a look at what we call the heating curve. All right, so we have a graph here. On the y-axis, that's the one going top to bottom, has the label of temperature. So our temperature increases, and our x-axis, going from left to right, is the amount of energy that we put into the system, or the amount of heat, okay? Now, we can start at 0, 0. If we start 0, 0, we're at the bottom left-hand corner, okay? Now, here's something interesting about liquid or compounds in general. As we heat it, our temperature goes up and we add heat, okay? And in this area, starting from the bottom of the corner to the point where we're going to start hitting a plateau, it is totally all solid, whatever material we're looking at, okay? And so all the energy that's happening here is basically being melting the solid content. We're dissolving the liquid. Then what happens is as we continue to heat, we hit a plateau. Okay, so from this point to this point, we add more energy, and guess what? Our temperature doesn't increase; it stays the same. At that plateau, we have a mixture of solid and liquid. All that energy is being utilized to convert that solid into the liquid phase until such time that all solid has been converted to liquid. And guess what? We have another increase in temperature. It rises. Now, we could say this is water. If that's the case, it could be 100 degrees, and we hit the second plateau. Now, during the rise, we have 100% liquid. Until that point that we have given enough energy to convert some of that liquid into the gas phase, and that's where we hit our second plateau. In that plateau, we have a combination of liquid and gas. All of that energy that you put into the system is not used to increase your temperature. It is used to break up those IMF interactions, break them apart so they can go into the next phase. So what does that tell you about heating a pot of spaghetti? Can you deduce anything here about heating a pot of spaghetti and you got it boiling? Let's assume that's water. Does that graph tell you anything about boiling water?
Be the reason why it takes so long to actually for it to start boiling.
Well, that could be related to, let's say we're talking about water. This water would act like this. That could be related to how much water you have. Obviously, if I got a little saucepan of water and I want to say boil a cup of water versus boil a gallon of water, it will take longer to obviously get the water that has a gallon to boil. So quantity it does have a factor as far as time is concerned, okay? But whether I'm boiling a cup of water or a 10,000 gallons of water, water boils at 100 degrees. Both of them will boil at 100 degrees, and both of them will have the plateau, okay? But you can do this. What you can take away from this plateau here is that once you got your pot of water boiling for spaghetti, no need to turn it up anymore. You're not going to get that thing to boil any quicker or faster. Once it's boiling, that's it. You got a plateau right here. There's your plateau. Of whatever temperature of water is 100 degrees Celsius or 212 Fahrenheit. And so if you're down here trying to turn up the heat a little bit on your burner, thinking you're going to get it to boil quicker or get more, you're just wasting your energy. So once it boils, just leave it that temperature, turn it back a little bit, save some SRP money, and just let it boil. Because you're not going to get that thing to boil or increase the temperature at all until such time that all that liquid has been converted to gas, and then the temperature shoots up to the next phase. Okay. All right. At the plateaus, both plateaus, all the energy you put into the system is being used to break up that intermolecular forces, the IMF forces that have that molecule. And water takes 100 degrees of temperature and energy to get that thing to happen before you get the water to boil. Some require even more, some up in the thousands of degrees. A lot of metals require 1,000, 2,000 degrees Celsius to get it to even to become liquid. Okay, because those forces are pretty hefty, pretty strong. All right. Let me see what we got here. And this again is the same graph, but the S to L, the S where the plateaus, that is where you have a mixture of both solid and liquid occurring. On the first plateau, the solid is being converted to liquid. All that energy you put into the system from the energy you put into the system from this point to this point, all that energy is being utilized to change the solid into the liquid. And then over here in the second plateau, all that heat and energy that you put into the system is being used to convert the liquid molecules into the gas phase. And that's why you don't see any increase in temperature. You have a plateau. Okay. All right. So this is basically what I just stated. Temperature remains constant. At the phase changes, all the energy goes into breaking the IMF interactions. And then your thing to remember here, we're not breaking bonds at those plateaus. We are breaking those forces that hold the molecules together, okay? So no bond breaking occurring there. That being said, congratulations. Chapter 14 is complete. One more to go, and we will do that next Tuesday. Okay. Other than that, God, I hope I started the